Hi, here's Jing and Yiping. Today we'll talk about functional space view of bounded norm in InniteWidth ReLU neural network. This talk will mainly cover these two following papers. The first paper will mainly deal with the one-dimensional case, and another will generalize it to high dimension. This line of research aims to categorize the geometry of the minimum norm interpolation problem for a two-layer neural network. They show that the minimum norm interpolation problem will generate a spline-like solution which come in a variety of flavors that can be categorized in terms of some differential operators. This line of research can be tracked back to a general principle which states that regularizing an inverse problem with a convex function yields solutions that are convex combination of a small number of atoms. Showed a similar representative theorem in reproducing kernel Hilbert space. Here are the references in inverse problem and some generalization for shallow and deep neural networks. First, let's talk about the problem setup for the two papers. We aim to calculate RF bar, which is in particular characterize how accurate a function can be approximated well with a bounded norm but infinite with ReLU neural network. Utilizing the homogeneity of the ReLU activation function, this paper simplified the minimum norm representing problem by the following ways. The idea is a similar construction with the large margin theory of neural network, which bind the max margin of L2 regularized neural network with one hidden layer and the max margin of convex neural network with one infinite hidden layer. It shows that the problem is equivalent to the L1 regularization over the last layer, which is tractable via the following green function argument. The mean theorem 3.1 is respected to weak derivatives. The proof idea is for any representation f, take its second order gradient and define it as alpha plus. The measure alpha that represents f is almost unique. The key is to minimize the one norm of alpha, and throughout a series of computations, we get a bound. Fitting a ReLU neural network can therefore be seen as the reverse of using green functions to solve a differential equation. We know the f, and would like to calculate the second order derivative u equals to f's second order derivative. We can do this by fitting an infinite width neural network and then reading off the second derivative from the resulting weights. Learning with norm regularized neural network is essentially equivalent to learning by minimizing the total variation of the derivative. How does fitting data while minimizing this total variation look like? These following theorems gives us an answer. The solution will become a spline-like interpolation result. The spline looks like this. Here is a figure. The left one is the linear interpolation, and the other one is fitted by a very, very wide neural network. You can see it is a spline interpolation. Okay. Then we will present the second paper to generalize the result to higher dimensions. The random transforms is the key of this paper. The random transforms represents a high-dimensional function f in terms of its integrals over all possible hyperplanes, and the dual random transforms maps the function to another function by integrating over the subsets of coordinates corresponding to all hyperplanes passing through x. Here are the precise definition of the random transform and its dual. The dual transform is also the adjoint of the random transform. The random transform is invertible for many common spaces of functions, and its inverse is a composition of the dual random transform or the adjoint of random transform by a filtering step in the Fourier domain. The theorem looks like this. This is a very classical result in the random transform literature. We also need to establish the following property of the Laplace and the random transform, showing that they can change the order. The fractional powers of the Laplacian is defined in the Fourier domain. The property is proved by a Fourier slice theorem. The Fourier slice theorem is here, and you can represent the Laplace transform in the Fourier space, and you can prove the Laplace and random transform can change the order. We also need to establish. Now let's go back to the infinite with two-layer neural network. The starting point to consider is let's calculate the Laplacian of the infinite with neural network, as what we have done in the one-dimensional case. The paper relates the Laplacian of an infinite with net to the dual random transform of its defining measure. We aim to define the representation cost of the function as a new R norm. Given this result, one might expect for an arbitrary function f, we should have the new norm defined as the L1 norm integral expression as given in the last slide. However, for many functions of interest, these quantities are not classically well defined. For example, the finite with ReLU net, which is a piecewise linear function that is non-smooth along each hyperplane, so its gradient can only be understood in the sense of generalized functions or distributions. And another case is that if your random transforms of R is not well defined, if your f is unbounded or it is not integrable along the hyperplanes. To conquer this paper used the duality to define a functional that extends to more general cases where the f is possibly non-smooth or non-integrable along hyperplanes. The main idea is to re-express the L1 norm as the supreme of the inner product over a space of dual functions. Here is the precise definition. With the new definition, this paper shows that the R norm of the function represented by a single neuron is actually the magnitude of A. Here is the calculation. If you're interested, you can go through it, but I will not explain the details. Then the general result for a finite with two-layer neural network can be obtained by the linearity of the definition. So here is the result. You can see here is the R norm of a finite with two-layer neural network. Next, we aim to show several useful properties of the R norm to understand how the interpolation result the neural network gives us it shares. As an example, the R norm is one homogeneity and satisfies the triangle inequality, its translation and rotation invariance. At the same time, the spiky functions will necessarily have a very large R norm shown by this lemma. For a generalization perspective, the fact that the R norm blows up for spiky functions with constraints is a desirable property, since otherwise the minimum norm fit to the data will be spike on data points. In particular, this is what would happen if the representation cost evolved derivatives lower than d plus 1. This is because of the trace inequality for the Sobolev functions. And so this tells us if you use the R norm to interpolate the data, you will finally give out a very smooth function instead of the spiky functions. The paper also showed the smoothness requirement of the R norm are also reflected in the Fourier domain. In particular, they show that for a broad class of function in order R norm to be finite, the Fourier transform of f must decay rapidly along every race. This tells us that the neural network will interpolate a smooth function. This is a good generalization property. Okay, this paper also relates the R norm to the very common function spaces as an example, the Sobolev spaces. It shows that the space of the functions with finite R norm is dense in the space of all functions, in the sense that it contains a full Sobolev space. This paper also provides a lower bound of the R norm. All these theorems is very easily be proved by the definition of R norm, and for the Fourier cases, you just need to rewrite the Laplacian in the Fourier transform. Okay, so how it is useful? Using the lower bound of the R norm, the paper shows that we can prove a depth separation result. It's an effort to understand the power of deep neural networks beyond the two-layer one. Much works have shown that some functions can be much more easily approximated in terms of the number of required units by deep neural network compared to a shallow ones, including results showing how functions that can be well approximated by three-layer networks require a much larger number of units to approximate if using a two-layer network. This paper also shows that, also in terms of the norm, such a depth separation exists for ReLU nets. Recall that any precise linear function is divided into small regions separated by a finite number of boundaries. Each boundary is a d-1 dimensional and contains a unique hyperplane. Hence, with every boundary, we associate with the unique up to the sign unit norm to the hyperplane containing it, which we call the boundary normal. Additionally, in the case that the compactly supported piecewise linear function, every boundary set that touches the complement of the support set, we call it an outer boundary. Otherwise, we call it the inner boundary. This paper shows that F is everywhere convex or everywhere concave when restricted to its support, and at least one of the inner boundary normals is not parallel with all outer boundary norms can't be represented by a finite norm two-layer neural network. But they can be represented by a three-layer one. How they prove this is using the lower bound to show that the R1 norm of this function should be infinitely large, but at the same time, it can be represented exactly by a three-layer neural network. There is also another ongoing debate in the community on whether the neural network learning can be simulated or replicated by the kernel mechanisms with a right kernel. In the context, it is interesting to ask whether the inductive bias we covered can be captured by a kernel norm. Actually, this paper gives a no answer. They prove that the R norm can't be represented as a RKHS norm. The proof is very simple. It's like they construct two functions f1 and f2 that doesn't satisfy this equality, which should be satisfied in the RKHS norm. In short, the two papers showed us how an InniteWidth neural network with constraint norm look like in function space. In one-dimensional cases, it's a spline, and the second paper used the random transform to generalize it into higher dimensions. This view also gives us some answer to the question like depth separation and the kernel and active regimes. Thank you for listening.